It is used to analyze the performance of an algorithm. How we are going to measure it? We are measuring it as a best case, average case and worst case. Next we have matrix multiplication. We are getting big O of n cube, so that we can say cubic time. Here I am taking f of n and g of n as a function. Hello everyone. Welcome to the Unit 2 session of the subject Design and Analysis of Algorithm. So we have in Unit 2 asymptotic notations. Today we are going to discuss regarding the asymptotic notation. Myself, Chandana C, Faculty of BCA, Vidhyaashram First Grade College, Temple of Excellence, MYSURU. So let us have a look into the content of today's session. Today we are going to discuss regarding the topic asymptotic notations and their basic efficiency classes. Next we are going to discuss about big O notation, omega, theta, and also we are going to discuss regarding the mathematical analysis of non-recursive and recursive algorithms. So these are the today session contents. Firstly, we move on to the asymptotic notations. So what are asymptotic notations? Asymptotic notations are mathematical tools. So these are mathematical tools used to analyze the performance of algorithms by understanding how their efficiency changes as the input size grows. So these are the mathematical tools. Asymptotic notations are the mathematical tools. It is used to analyze the performance of an algorithm. So these notations help in analyzing and comparing algorithm performance, especially for large inputs. If the input of an algorithm increases, it takes more time to get the result. So hence the comparison and analyzing of algorithm performance depends upon the large inputs. Nextly, we have three mainly asymptotic notations, that is big O, omega and theta. Let us discuss each one by one. Next, there are three mainly asymptotic notations which are discussed in the upcoming slides, that is big O, omega and theta. So by using these notations, these three notations, we can characterize algorithms based on their worst case, best case or average case. In asymptotic analysis, we evaluate the performance of an algorithm in terms of their input size. As I said earlier in the first slide, so depends upon the input size of an algorithm, so we can calculate the running time of an algorithm. Here I am taking f of n and g of n as a function, two functions. These are non-negative functions which are defined in a set of natural numbers. The algorithm running time, that is I am taking as t of n. The running time is measured in t of n, is usually indicated by its basic operation count, that is c of n and g of n. So some simple function to compare with the count. So here I am taking two functions, that is f of n and g of n, and I am taking to count the time in the form of t of n. So next is time complexity. How we are going to measure it? We are measuring it as a best case, average case and worst case. If the key is the first element of the list, so if I have 5 elements in an array, if the key, what I am searching, if it is present in the first element, I am going to say it is a best case, that is theta of 1. Its time complexity is theta of 1. Next, if the key is somewhere in the middle, then I can say it's the average case. In the worst case, if the key is the last element or not present in the list, if I keep on searching for that key, if it is not present, it takes a longer time, isn't it? Then I can say it's the worst case of an algorithm. Next, we will move on to the big O notation. Let us discuss one by one regarding this notations. That is, firstly, we are going to discuss about big O notation. So what is this big O? So this represents the upper bound. You can see in the figure. So it is represented in the upper bound. The C of G of n is present upper bound than the function of the running time of an algorithm. It gives the worst case complexity of an algorithm. So below expression can be described. So here we have a expression, that is big O of G of n if there exists a positive constant C. See here the positive constant C is exists. So that is lies between 0 and G of n. So that is lies between. So here the function is lies between the 0 and C of G of n for sufficiently large n. So we have a expression, that is big O of G of n is equal to f of n. There exists a positive constant such that that is C and n naught. If 0 is less than f of n, that is less than C of G of n for all n is greater than or equal to n naught. So we can see here how they are expressed in the expression. So that is 0 is less than or equal to f of n, that is less than or equal to C of G of n. This is how we can express the worst case of an algorithm. So for any value of n, the running time of an algorithm does not cross the time provided by big O of G of n. It does not cross this. Since it gives the worst case running time of an algorithm, it is widely used to analyze an algorithm, as we are always interested in the worst case scenario. So always we will be interested in the worst case scenario. So whichever the algorithm we take, firstly we will look into the worst case analysis. How much the algorithm takes the time to execute. If I take an example for a big O, that is I am taking here quadratic equation, that is 3n square plus 5n plus 2. So in this example, I am taking an example, this quadratic equation. In this, it ignores all the lower bound functions and it considers only the upper bound, that is 3n square. 3n square. As it is a quadratic equation, it ignores this constant also and it concentrates only on the n square. Hence, we can say the time complexity of this equation is big O of n square. So like this, we can calculate the time efficiency of an algorithm. Next, we will move on to the omega notation. So this represents the lower bound. As big O represents the upper bound, this omega represents the lower bound of the running time of an algorithm. So it provides the best case complexity. So you can observe here. So f of n lies above the C of G of n. Or we can say C of G of n lies above the f of n. So hence we can say it represents the lower bound. The below expression can be described as a function. F of n belongs to the set of omega of G of n. So there exists a positive constant C such that it lies above the C of G of n. We can observe here the f of n is lies above the C of G of n. So for sufficiently large n. So for any value of n, the minimum time required by the algorithm is given by the omega of G of n. So here they have given omega of G of n. Considering the omega notation, if I take an example for this, that is f n square plus n. So by considering the lower bound, we can write omega of n. So this is how we can write the complexity using the omega notation for the given expression. Next we will move on to the theta notation. It encloses the function from above and below. So we can observe in the diagram or a given figure, f of n is between the C2 G of n and C1 G of n. Since it represents the upper and lower bound. So hence this is representing the upper and lower bound of the running time of an algorithm. So it is used for analyzing the average case complexity. So for example, if I take a linear search, if the key element is present in between the given array, so it takes the average time complexity. So based on that, we can write a function g of n, theta g of n is given by the relation like this. Theta g of n, f of n, there exists a positive constant. So positive constants we have C1, C2 and N0. So such that we can write the expression as the 0 is less than or equal to C1, g of n is less than or equal to function f of n is less than or equal to C2, g of n. If a function f of n lies anywhere in between for all n greater than or equal to n0, then it is asymptotically tight bound. We can say it is asymptotically tight bond. So here it is looking like a sandwich, isn't it? It is tightly bound between the C1 and C2. Next, we are going to discuss regarding the basic efficiency classes, that is time complexity. So the different examples means searching, sorting, anything. We have taken certain examples and we have their time efficiency. For that time efficiency, we have given certain name. Let us look into that one by one. Firstly, we have an example of accessing an array element. So for that, we have a efficiency class big O of 1. That we call it as a constant time. Next, we have binary search. For that, we have big O of log of n. We are telling that logarithmic time. Next, traversing a list, we have big O of n. That is, we say linear time because it should search throughout the n number of elements. It needs to search n number of elements. That's why we say linear time. Next, we have merge sort and heap sort. So, for that we are getting big O of log n. That we can say linear rhythmic time. Next, we have bubble sort and insertion sort. We are getting for that big O of n square. That we can say quadratic time. Next, we have matrix multiplication. We are getting big O of n cube. So that we can say cubic time. Then for solving the travel salesman problem, we are getting big O of 2 power n. That we can say exponential. As it is 2 power n, we can say exponential time. The last we have the solving permutations, that is factorial time. That is by getting the big O of n factorial, we can say the factorial time complexity, the name we can tell. So these are the some time complexities for the different examples we are getting. As we come across the different time complexity, how we are going to visualize that hierarchy, how we are going to visualize that hierarchy from fastest to slowest. So the algorithm which is going to execute fast to the lowest. So we are going one by one. That is, we can represent it like this. Big O of 1 less than or equal to big O of log n. So like this, we can represent the visual hierarchy as per the time efficiency table. So these asymptotic notations, they simplify the analysis of algorithm by focusing on large inputs. They ignore the constants and lower order terms, and understanding the efficiency classes helps to choose the right algorithm based on time and space trade-offs. Next topic is the mathematical analysis of non-recursive algorithm. We have some general plan to analyze the time efficiency of the non-recursive algorithms. So firstly, we need to decide on a parameter, so which indicates the input size. Parameters, what we are writing within a brackets. So firstly, we need to decide how many parameters we need for this problem. Next, we need to identify the algorithm's basic operations. So which are the basic operations we are going to use in this problem, that we need to identify. Next, check whether the number of times the basic operation is executed depends only on the size of the input. Next, if it is also depends some additional property, then we can say the worst case, average case, and if necessary, the best case. We need to check how many times the basic operation is executed in a program that depends only on the size of inputs. Then we can tell whether it's running in best case, worst case, or average case. Next, we have set up a sum expressing. So after calculating the basic operations, how many times it has executed in the program, next we need to calculate the sum expressing. We need to set up sum expressing, that is the number of times the algorithm's basic operation is executed in the program. Let us discuss the next plan. So we have the plan 5 here. So using the standard formulas and rules, so some manipulation we need to do to form what? To establish for the order of growth. So these are the some of the plans we need for the mathematical analysis of non-recursive algorithm. So next, consider the simple example. We have largest element. Need to find the largest element in a list of n numbers in an array. We need to find the largest element in a list of n numbers in an array. So assume that the list is implemented as array for simplicity. So here I have a simple example for the non-recursive algorithm, that is to find the maximum element in an array. So how I am going to write? I have a algorithm is a keyword. Next, followed by the problem name. Next, I have a set of array values. Some n-1 array values I am giving. So these are called parameters. Next, within a double backslash, this is for user reference, it contains the name of the problem. Determines the value of the largest element in a given array. What I am going to do in this algorithm? I am going to determine the largest element in an array. Next, what I am giving as an input? I am giving an array from 0 to n-1, the index of the real numbers. Next, what is the output I am going to get? The value of the largest element in A. So here is the body of the algorithm. Firstly, I am going to assign the A of 0. For example, if I take a array 10, 5, 20, then 4, 2. So this is my array elements. 10 has the first element has an index A of 0. Next is A of 1. So like this, it moves on till how many numbers I have? N is equal to 5. It is 0, 1, 2, 3, 4. See, I have n is equal to 5, but I am getting the index n-1. So that is here I am telling for I is equal to 1 to n-1. Do what you should do till 1 to n-1. What I should do? So compare each element with the maximum value. So for what I did in the initially, the A of 0, the index A of 0, what is there here? 10. The value 10 is there. Here this 10 I have assigned to max value. I am considered as a maximum value 10. Next, from 1 to n-1, what I should do? I should compare each and every element. So compare 5 with 10. Is it greater? No. Then I plus plus. So I value increments. Then it moves to 2. So here I have a 20. Compare 20 with 5. Is it greater? Yes, it is greater. Then the max value will become A of I here. What is now I? It is I plus plus. Now it is 2. So A of I is 2. The value A of I is 2. So that is 20. So now the max value is 20. Max value is 20. Again, I plus plus. So now I value is 3. Compare 4 with 20. The 20 is the maximum value. The result will be false. Next, I plus plus. Now the compares with the 2 with 4. No. So what is the maximum value now? 20. So return. A of I is equal to max value what I have written. So that will be written in the last. That is maximum value is 20. So it checks through n minus 1 from 1 to n minus 1. So this is how the searching the maximum element in a non-recursive algorithm works. Next, what is the analysis we will come across this by searching the maximum element? The analysis was input size here is the number of elements in the array, isn't it? That is n. How much I have given? N is equal to 5. The value of n is 5. There are 2 operations, isn't it? So we checked each and every element with the maximum. That is the first element. We checked all the other elements in an array. We checked with the first element. So that's why we used comparison operation. That's why we used comparison operation. And we assigned the maximum value to A of I. We assigned, right, the max value. So hence we used assignment operator and comparison operator. So hence we used assignment operation and comparison operation here. So see here, comparison and the assignment. So in the algorithm, the assignment operator is denoted in the left side arrow. The comparison operation is considered as the algorithm's basic operation because the comparison is executed on each repetition of the loop and not the assignment. So assignment, initially we assigned a max value, isn't it? The first element to the max value. But afterwards, the most used operation is comparison. The number of comparison will be the same for all the arrays of size n. So let C of n denotes the number of times this comparison is executed. So before the sum for C of n is calculated by using the formula, C of n is equal to sigma of I is equal to 1 to n minus 1. So hence we will get C of n is equal to n minus 1, that is belongs to theta of n. So therefore the efficiency of the algorithm is theta of n. So this is what we analyze for the finding the maximum element using a non-recursive algorithm. Next, we will move on to the mathematical analysis of recursive algorithm. So in the last slide, we discussed regarding the mathematical analysis of non-recursive. Now we are going to discuss regarding the mathematical analysis of recursive algorithm. So what are the general plans? Let us have a look. Decide on a parameter that indicating an input size. So here also we need to decide how many parameters we are going to give or enter to the algorithm. Next, identify the algorithm's basic operation. So here also we need to identify how many basic operation we need for the calculations. Next, check whether the number of times the basic operation is executed can vary on different inputs of the same size. If it can, the worst case, average case, best case efficiency must be investigated separately. So based on the number of times the mathematical operation executed, we can define whether it's a worst case, best case or average case. Next, set up a recurrence relation with an appropriate initial condition for the number of times the basic operation is executed. Next, solve the recurrence or at least certain order of growth for its solution. So these are some of the general plans for the non-recursive algorithm. Next, we have an example for non-recursive is factorial n. We need to find out the factorial n. If factorial n, for example, if I take 5 factorial, so what is the formula I need to calculate? 5 into 4 into 3 into 2 into 1. So that is 5 means n into 4 means what? 4 means it becomes n minus 1. N minus 1 into n minus 2, n minus 3. So it goes on, n minus 4, isn't it? So to find out the factorial 5, I have the formula, this one. So how to write using a algorithm? I have a keyword, then I have given a f of n. That is, n is a parameter here. Here f is a name of the problem, then algorithm is a keyword. What I am going to do? I am computing n factorial recursively. Recursively means what? A function which calls number of times itself within a program. Then what are the input? Non-negative integer, that is n I am going to give. Just I am giving 5, that's it. What is the output? The value of n factorial, that is 5 into 4 into 3 into 2 into 1. So what is the answer? 5 4s are 20, 23s are 60, 62s are 120. So 120 is my answer. So if n is equal to 0, if I have given 0 factorial, then what you should return? Return 1. So else you do this one, that is n into f of n minus 1. Okay, so this is the algorithm. Here we consider n itself as an indicator for this algorithm input size, that is 1. The basic operation for the algorithm is multiplication, isn't it? Only one mathematical operation we used to find the factorial of a given number. So whose number of executions we denote m of n, that is multiple of n. Since the function f of n is computed according to the formula, so what formula used to compute the factorial n? So n into n minus 1. For all n should be greater than 0. If n is equal to 0, it was written only 1 as the answer, isn't it? For all the n greater than 0, it computes using this formula. So it calculates the factorial of a given number using this formula. The number of multiplication, that is m of n, is needed to compute it. Hence, we can write the formula for this recursive algorithm like this, that is m of n minus 1 plus 1. Why m of n minus 1? To compute f of n. For this, we are adding 1 to multiply f of n minus 1 by n. For all, n should be greater than 0. So after computing the n factorial for a non-recursive algorithm, so we are going to analyze the algorithm, that is m of n minus 1 multiplications are spent to compute f of n, and one more multiplication is needed to multiply the result by n. Needed to multiply the result by n. Therefore, the efficiency of algorithm is big O of n. Mathematical operation is used number of times, that is n minus 1 times. By this, I am ending this Unit 2 session. Today we discussed regarding what are asymptotic notations, what are the three main asymptotic notations, and we did the mathematical analysis of recursive and non-recursive algorithms. In the next session, I am going to discuss regarding the Unit 3, which contains the introduction to brute force approach. So in that approach, so using the brute force approach, we can solve the selection sort, bubble sort and sequential search. Thank you.